Welcome to Microlecture 20, conformational analysis. We're just going to be using Newman projections to solve some alkane conformational analysis problems. Okay, so let's solve this conformational analysis problem. The first thing it's asking is to draw the skeletal structure of the compound. At first, when I read this question, I was thinking all the compounds are the same, and you might have made that mistake too. But a quick carbon count will tell you that they are not. So it's always good to count carbons. I see the carbon in the front, okay, and I see the carbon in the back. So that's 2 carbons, and then all the carbons coming off. So that's 3, 4, 5, and so I see a 5-carbon compound here. Let's do the same thing next door. I see the carbon in the front. There's a carbon in the back, and I see all the other carbons. So 3, 4, 5, 6. So this is a 6-carbon compound. So we're going to draw the skeletal structure of the compound represented by each Newman projection. So this is a lot. So compound number 1, I'm going to draw a dot just where I had put the dot on the Newman projection, and I see that there's 2 CH3s coming off of that carbon, so I'm going to draw one of them here and one of them here. Now the rest of the molecule is in the back, and we're viewing down that bond. So here's my eyeball, and I'm viewing down that bond. Okay, so the carbon in the back is right here. And so off of that carbon, I've got 2 hydrogens pointed upward and a methyl pointed downward. And so the compound is this. And I just check that I have the correct number of carbons. I do. 1, 2, 3, 4, 5. It's a 5-carbon compound. So the skeletal structure for number 2, I'm going to use the same technique. I'm putting a dot where I have the dot on my Newman projection, and I see that I have 2 CH3 groups again. So I'm going to draw those in. I have the bond going to the rest of the molecule in the back. Off of that rear carbon, I have 2 CH3 groups. 1, 2. So that would be the skeletal structure for number 2. It turns out number 3 is the same compound. So I've got the carbon in the front, 2 methyl groups, if you will, and the carbon in the back, okay, has 2 methyl groups as well. So these 2 are the same. And then we can do carbon or molecule number 4, which is a unique molecule from the rest of them. So we've got the carbon in the front, and it has a couple of methyl groups on it, and then we've got the carbon in the back, and that carbon in the back has just 1 CH3. There's 2 hydrogens. And so that would be this compound. All right. So we've drawn skeletal structures for all of them. The next thing it asks for is to name the compound. And so that's a matter first of finding the longest continuous carbon-carbon chain. So find the parent. Once you have the parent, you can name all the substituents on it. So I'm going to number this parent like so that I put the methyl group, the substituent, on the number 2 carbon. If I numbered starting with the one numbered 4, I would have a substituent on the 3rd carbon. We always want to lower the numbering, so that wouldn't be good. This is a 2-methyl butane. We'll do the same thing again to name each molecule in turn. the way we write it when there's two of the same group is we put the numbers first separated by commas. So there's two methyls. They are on carbons 2 and 3. So it's 2, 3. And then we have a prefix. Di, tri, and tetra are used in this course. So di is for 2. Since there's two methyls, it's a dimethyl. And the parent is still butane. We see that that's the same compound as the one in number 3. So these are both 2,3 dimethyl butane. And the last molecule is a 2,2. On carbon number 2, we have 2 methyls, 2,2 dimethyl. The last part of the problem asks us to draw the most stable Newman projection. So that's going to be a staggered Newman projection, and these are all staggered Newman projections. So we just have to look at the Newman projection that's drawn and say, is this the most stable that it possibly can be? And if not, then let's rotate about the rear carbon to make a more stable staggered drawing. And so in this first example, I'm seeing two methyl groups that are as close as they can be without eclipsing. So when they're that close to each other in a staggered position, 60 degrees away from each other, that interaction is called gauche. So those two methyls are in a gauche position relative to each other. This costs steric strain. And so I can rotate about the rear carbon. And so I'm going to redraw the Newman projection. And I'm going to rotate about the back. So on the front, I have a CH3, and a hydrogen. And on the back, I've got a CH3. Let me redraw just to make it a little bit more clear. I've got a CH3, a hydrogen, and a hydrogen. And I'm going to put those hydrogens here. Okay, so I've got 3 CH3s total. And I see I still have a gauche interaction here. Let me try one more time, keeping the front the same. So methyl upward, a methyl downward and to the right. Fix that one. And then a hydrogen atom. So I always keep the front the same. And so this time I'm going to have hydrogen, and then CH3 right there. And this one is very costly. We've got a gauche interaction right there, but then we've got another gauche interaction right there. So we've got 2 gauche interactions. So that's definitely not going to be the most stable. And that's it for staggered conformations. There's only 3 possibilities. So it turns out that the one that is already drawn is one of the 2 that are the most stable possible. Right? And so I'm just going to circle this one here and say that is most stable possible for this compound. All right, and let's do the same thing for 2,3-dimethyl-butane. We're going to look at the way that it was drawn already and see, is there another way? Certainly we know we can draw the staggered conformation 3 different ways. So being that these two are the same, that kind of reduces the labor that we need to do for this. So both of these have the same answer. All right, and so what we're seeing for the way that it's drawn in number 2 is that we've got a lot of Gauche interactions. We've got this Gauche interaction, this Gauche interaction, and this Gauche interaction. So there's actually 3 Gauche interactions there. So that's going to be probably the least stable staggered conformation that you can have. In this one I've got 2 Gaussian interactions total. One right there, one right there. And so there's only one more left. So let's just draw it down here, keeping the front the same. So my hydrogen is down and to the left. The other 2 are methyl groups, CH3s. And I'm going to rotate to get the hydrogen pointed down, the CH3 up and to the right, and the other CH3 up and to the left. That's the only other one that's not drawn. And we see again, we end up with a very high energy situation where we have 3 Gauche interactions. And so that's not ideal at all. And so the one that is going to work the best is actually one of the 2 that's already drawn, and it has only 2 Gauche interactions. So that one is the most stable. And then the last one for this molecule, one of them's already drawn. Let's analyze that one first. And it has a Gauche interaction here and a Gauche interaction here. So it's got 2 Gauche interactions. And so the question is, can we do any better than that? So let's draw the other 2 possibilities down here. We see that we have 3 methyls in the front, so let's just keep that way for both of these. And then in the back, on the structure already provided for number 4, we've got the methyl pointed downward. So let's move that around clockwise, let's point it upward. The other 2 are hydrogens. And then in my last structure, let's move it to the right-hand side. And the other 2 are hydrogens. So what kind of interactions do we have here? Well, we still have Gauche interactions. So there's the Gauche interaction right there, and a Gauche interaction right there. There's a Gauche interaction right there, and a Gauche interaction right there. Okay, and so all of the possibilities are identical. And so we can just write that. There is no most stable form because they're all equal energy. Okay, with 2 Gauche interactions. Okay, so this problem asks us to draw all possible staggered Newman projections for the compound shown, where the starred or carbon with the asterisk is in the front and the bulk of the molecule is in the back. And then we'll name the compound and circle the least stable Newman projection. All right, so the carbon with the asterisk is in the front, and so that's why the Newman projections have the asterisk there, just to remind us of that. So that carbon has 2 CH3 groups and a hydrogen. And so I'll just randomly choose for the first structure, say this one. And then in the back, So I'm going to highlight that back carbon, and just to remind ourselves, everything coming off of this circle is something coming off of that highlighted carbon. So we have a carbon with 3 other carbons attached to it. That's called a tert-butyl group. And so we've got a tert-butyl group, and we can go CCH3, like that. And in addition, we've just got hydrogen atoms there. All right, so this would be, if I was labeling all of the carbons and hydrogens and not using a skeletal depiction in my Newman projection. If I wanted to draw the same Newman projection but use a skeletal depiction, in that case, all hydrogens must be labeled, otherwise they look like methyls. And so let me redraw it. I'm kind of flipping it on its head, because I like to draw the front carbon with the bond pointed upward, and then the 2 other bonds going to the right and to the left. So I'm going to kind of take this molecule and kind of flip it on its head. And so the CH3 is pointed up, and then I've got the other CH3 here and the hydrogen there, and then in the back I've got the CH3 and 2 hydrogens. Okay, now I can convert that to skeletal form. So instead of having just CH3, I can just have the bond like that, just like we would in a skeletal structure. Same for that. And then for the tert-butyl group, what that's going to look like in skeletal form is this. All right, so that's the same Newman projection, just drawn a little bit simpler. So I'm going to rotate the back carbon. Normally we do this in 60-degree increments, but 60 degrees will get you to an eclipsed conformation, and we're looking only for staggered. So we're going to do 120-degree rotations. And so if I rotate 120 degrees, let's see what we get by doing that 120-degree carbon-carbon bond rotation. And because I like my mine better, I'm going to not use the template ones. I prefer to always have the front carbon look like kind of like a peace sign or like a Mercedes symbol. That just helps me to always have it the same way. You should be able to interpret it either way, but for drawing it myself, I prefer to do this. So all I'm going to do is rotate around the back 120 degrees. So that's going to put this tert-butyl group right where that hydrogen is. So the front is the same. This is a hydrogen atom. In the back, I'm going to move my tert-butyl group over here. And then this will be a hydrogen, and this will be a hydrogen. And then we'll do that one more time. The tert-butyl group is now going to move over to where that hydrogen is. Again, these are 120-degree carbon-carbon bond rotations to get from one staggered conformation to the other. So tert-butyl here. Let me make sure I have my front drawn first. So methyl hydrogen. Okay, tert-butyl, and then hydrogen and hydrogen. Okay. So those are all the staggered conformations for the structure that's drawn. And the last thing to do is name the compound. Oh, 2 more things to do. Name the compound and circle the least stable. Newman projection. Alright, so naming the compound, we would want to count the carbons in such a way as to have the greatest number of branches, and also have those branches be on the lowest carbon numbers as possible. So I see that my parent is this, which is a pentane, 1, 2, 3, 4, 5 carbons long. And then the question becomes, do I number it from the left or number it from the right? Knowing that I want to minimize the numbers of the substituents, I would go this way because I have 2 substituents on carbon number 2. If I went the other way, I would have 2 substituents on carbon number 4, and I would not be lowering the numbering. So minimize the numbers given to substituents. Okay, so I see 1, 2, 3 methyl groups, and remember when you have more than one of the same group, you have to use the prefixes. So prefixes exist, there's a lot of them, but we would only see di for 2 of the same thing, tri for 3 of the same group, and tetra for 4 of the same group. So we have 3 methyls, so we would write this 2, 2, 4, because the methyls are on 2 of them on carbon 2 and 1 on carbon 4. So trimethyl, and a 5 carbon long parent is a pentane. Alright, so we have named it. And we are ready to answer this last part, which is circle the least stable Newman projection. So we're going to look for interactions that are destabilizing to the structure. I see in this first structure a Gauche interaction between tert-butyl and methyl. In the second structure, I see a Gauche interaction between tert-butyl and methyl. And then in the third structure, I see 2 Gauche interactions between tert-butyl and methyl. And so that will certainly be the most costly. And so I'm going to go ahead and circle that one. It says to circle the least stable Newman projection. So this is the least stable.